Okay, in this lesson we're going to talk about a new kind of proportion, inverse proportions. Last time was direct proportions, now we're going to do inverse proportions. Okay, so before I talk about what those are, I want to kind of prep you for it, so to speak. Give you two problems to think about and say, tale of two proportions. So here's a proportion. Biff. Biff is driving. He drives 800 miles in 15 hours. Okay, he's going somewhere far away. Anyway, and it says, okay, if he keeps going at this rate, how much longer to go another 500 miles? So he hasn't even reached where he's going yet. So he's gone 800 miles. It's taken him 15 hours. He wants to go another 500 miles. So how many more hours is this going to take? That's a practical question if you've ever done a really long road trip. So anywho, what do we got here? We got kind of like a proportion. You get, what in the world? It's a proportion, right? Because basically they're giving you a couple numbers and they go together. Now they're not saying, hey, it's directly proportional, but we can ask ourselves, is it? Directly proportional would mean if I want to go twice as many miles, will that take twice as many hours? Yeah. And if I only want to go half as far, will that only take half as long? Yeah. So we do have a direct proportion relationship between the miles and the hours, between the distance and the time, if you will. It is a directly proportional relationship. And that means we can start doing things like this. Hey, the ratio of 800 miles to 15 hours has got to be staying the same. In fact, they're even saying it right here at this rate. Keep the rate the same, which is keep the speed the same, keep the miles per hour the same, keep the ratio the same. It's all different ways of saying the same thing. So anyway, we're going to keep that the same. So again, it took them 15 hours to go 800 miles. I wrote that there. And he's going to go another 500 miles. And how long is that going to take? Now notice that when you're setting up the proportions, or I guess we noticed this last time technically, but you want to keep the rhythm the same, right? So you want it to sound the same. 800 miles, 15 hours. 500 miles, how many hours? Miles over hours. Miles over hours. That has to be the same. Make sure it's the same. We're trying to keep the ratio of miles over hours the same. Another way to say the same thing is miles across from miles, hours across from hours. However you want to look at it, however you want to say it, it's up to you. But anyway, there's our nice proportion. I guess we're ready to go, right? Remember the old rule of three? You do the old, take the two numbers that share a diagonal, those two numbers, multiply them together. So 15 times 500, and then we'll divide by that other number, 800. And when you do this, I did this, right? Yep. You get 9.4 hours. Okay, 9.4 hours. Now, here's the point I want to make. Always, that's supposed to be a star. Always ask yourself, when you do a math problem, does this match my expectation? Is it reasonable according to what I was expecting? Well, you have to ask yourself, what was I expecting? What I was expecting was that since it's directly proportional, remember it should be like the same ratio here as here. So 800 to 500, right? What do you want to say? A little more than half? It's a little more than half. I mean, I'm just talking roughly here. I'm not trying to do math again. I'm just trying to set up my expectation. So it's a little over half, right? I mean, half of 800 is 400, so it's a little more than half. So that means I expect this to be a little over half as well. And half of 15 is 7.5, so that's a little more than half. So yes, it's matching my expectation. You always want to do this kind of thing. Is it matching my expectation? Okay, well, that's cool. I hope this is all feeling groovy. Now let's do another problem that kind of looks similar. Biff is driving again. So it says Biff drives 60 miles an hour and it takes him 40 minutes to get to work. That's not so bad, 40-minute commute. But maybe he's late for work and he's like, if I increase my speed to 70, I wonder how many minutes that'll take, right? How many minutes can I trim by going an extra 10 miles an hour? That's another practical question. So let's see now here. The two numbers that seem related are the 60 miles per hour and the 40 minutes, right? Those are the same situation. When he drives 60 miles an hour, it takes 40 minutes. Now, I'm going to warn you here. Right now, I am thinking too fast. If you think too fast, you might be thinking like this. Hey, 60 miles an hour takes 40 minutes. Okay, that's the ratio here. Let's keep it the same because he's going to go 70 miles an hour. So how many minutes is that going to take? Well, if you do the rule of 3, ROT for rule of 3, X is going to be, you'd multiply the 40 times the 70, and you would divide it by the 60, and you would get 46.7 minutes. Cool, we cranked out another homework problem. Circle it, go home, let's get out of here. Wait. I was saying that we should always do this, like always. Does this match our expectation? And I'm going to ask you, does that match your expectation? Sure doesn't match mine. What? Because when I go 60 miles an hour, it takes me 40 minutes. Okay. So if I go faster, is it going to take more than 40 minutes? No, it's going to take less than 40 minutes. That's going too fast. Cross that out. I hope you didn't copy that, because if you did, that's going to get in your muscle memory and it's going to be a problem. But you want to erase it from your muscle memory by never, ever, ever doing it that way again. What you got to do is you got to say, there's something at issue here. At issue. See, we should have asked ourselves before we set this up this way as a nice little ratio of miles per hour over minutes. We should have asked ourselves, is this a direct proportion? With a direct proportion, one number gets big, so does the other. If the 60 miles an hour goes up, so will the time. If I drive faster, it'll take longer. That's what a direct proportion is. But this is not a direct proportion because I don't want to have it take longer when I drive faster. This is what we mean. This is what we mean by inverse proportion. This is an inverse proportion. We expect exactly the opposite. As one quantity, QTY means quantity, as one quantity grows, the other shrinks. They go in opposite directions, in other words. Doubling one cuts the other in half. If I go twice as fast, it should only take me half as long to get there. Does that make sense? Doubling cuts the other in half. So this is not the same kind of situation as we had up here. This is called a direct proportion. This is called an inverse proportion. They're very different kinds of proportions. Now, since they're different kinds of situations, different kinds of proportions, they're going to have different kinds of setups. So here's the new setup. If you have an inverse proportion situation, if you have an inverse proportion, you have to use it this way. So I'm going to write it this way. Not 60 miles per hour over 40 minutes, but you would do it this way. 60 miles per hour times 40 minutes. So see how the setup switches. So instead of one over the other, it's one times the other. It's kind of like we were dividing, but now we're multiplying. You do the opposite because the situation is opposite. One's bigger makes the other one smaller. That's an inverse. You don't set it up like you do old-fashioned direct proportions. You set it up this way. And so the 60 miles an hour times 40 minutes is the same as the 70 miles per hour times X minutes. That's your setup. And if you solve that, 60 times 40, and then you'll have to divide both sides by 70, you will get, in this case, 34.3 minutes. And that is correct. Okay? Boy, maybe I should have written this part in a different color, because that's the important part right there. You have to, well, this is important too. At issue. Realize that you have an inverse proportion. You have to do that part yourself. Okay, not everyone's going to walk up to you and say, hey, it's an inverse proportion. I mean, sometimes you have to figure it out yourself and say, wait a minute, this helps. Does your answer match your expectation? Wait, I wasn't expecting it to take longer when I went faster. So it must be the other kind of proportion, right? It has to be. It's got to be one of those inverse weirdo proportion things. And I have to set it up this other way, over here, this way. This is how you set up an inverse proportion. Okay, so if I come back to the top of the page for a minute. Inverse proportion. That's what it means. Okay? It means the proportion is well, the variation is in the opposite direction. And here's, like I was just saying, no one's going to tell you, hey, it's an inverse. And especially when you go to take your Journeyman's exam. This was a question on I don't know if it was the real exam or if it was a practice of Journeyman's exam, but I had an old guy that doesn't work here anymore, an old electrician instructor, gave me this problem. He said, this is a good problem. This one was on the Journeyman's exam. So anyway, what's going on? You got a 40-tooth gear meshed with a 100-tooth gear. It's nothing to do with electricity, right? But it's on the Journeyman's exam under a section called Physical Reasoning. They want you to be able to know some of this stuff. So 40-tooth gear is meshed with a 100-tooth gear. The 40-tooth gear is spinning at 80 RPMs, revolutions per minute. So how fast is the 100-tooth gear going? Okay, I'm going to draw this first. You got a 40-tooth gear, so I'm not going to draw the 40 teeth, but just pretend that's a 40-tooth gear. Maybe I'll write it this way, 40 teeth. And it's meshed with what has to be a bigger gear. I mean, the teeth have to be the same size. So if you've got 40 teeth on one gear and 100 teeth on the other gear must be bigger. Okay, fine. So I got my two gears. Now, this, let's get a new color. The 40-tooth gear rotates 80 RPM. 80 RPM. So it's, spinning. And then the question is, how many RPM is this gear going? Now, it's going to be going the other way, right? But how many RPM is this one going? Now, you have to ask yourself the point. Does a, let's say, bigger gear, more teeth, spin faster? If so, that would be a direct proportion. Or is it the opposite? Does a bigger gear spin more slowly? Slower. If a bigger gear goes slower, that's an inverse. Because see what's happening. Again, are the things changing in the same direction or in opposite directions? Bigger gear, more teeth, goes faster. That would be direct. Bigger gear, more teeth, it goes slower. That would be inverse. Okay, so we have to decide for ourselves. Is this one of those standard proportions? Should I set it up like we usually do? Like we did last time, where we go 40 is it, or should I set it up this way, 40 times? I have to figure this out. So hopefully you kind of have seen gears meshed and spinning before, and if not, I encourage you to go find something with gears, or maybe your 10-speed bike or something. What you will see is that actually the bigger gear does go more slowly. And you may have seen this at some point. You got this big old gear over here going, spinning around, and then especially if you have a little gear, you can really tell. A little gear will just be going wee really fast, right? Because for this thing to go around once, right, this thing has to go around 1,000,000 times. Wee! So the little one's definitely going faster. Let me erase all that pink stuff. That's kind of getting weird. Okay. We have an inverse proportion. And since we have an inverse proportion, we're going to take these two numbers and we're not going to put one over the other. We're going to multiply them, because that's how you do an inverse proportion. So the 40-tooth gear goes 80 RPM. The 100-tooth gear goes how many RPM? We can solve. So it's 40 times 80, and you'll end up dividing both sides by 100 in order to get the x by itself. So 40 times 80, and then when you divide by 100, you get 32. 32 RPM. Okay. So when you get to the Journeyman's exam, make sure you remember that. What sorts of other things are inverse proportional? Well, a good example would be like a teeter-totter, seesaw type thing, right? This is inversely proportional in the sense that you put some kid sitting out here. If you're like big and heavy compared to the kid, if you sit out here, you're just going to go right to the ground. You'd have to sit closer in, right? So notice that we have this relationship here between this distance and your weight. This distance and your rate. And by the way, that's called torque. Distance times force is called torque. So the torques are the same, is another way to say it. But it's inversely proportional. The bigger guy has to sit closer. What else? I don't know. There's other things. So just kind of keep your eye out for these things, especially on homeworks and journeyman exams. So what do you say we get back to your book now, your electricity book, and start talking about the things you're going to see, the statements you're going to see in your electricity book. Things like this. Let's go back to blue. Things like this. The resistance of a wire. Remember last time it's directly proportional to length. Well, it's inversely proportional to its cross-sectional area. What does this mean? It means two things. It means here's a wire. If you make the wire have a bigger area, the cross-sectional area, this area, if you make a wire have a bigger area, the resistance goes down. If the area goes up, the resistance goes down. Now, why is that? Well, I think of it as like a straw. Which straw is going to be easier to blow through? It's going to be a lot easier to blow through a big straw, right? You can just blow all through the big straw. Whereas here you got to force it through to get the same kind of flow. Anyway, a bigger area has less resistance. So the setup when you're doing this kind of stuff is you should go something like, wait, I suppose I should put resistance first because they said resistance first, but the resistance in situation of wire 1 times the area of wire 1 is going to be the same as the resistance of wire 2 times the area of wire 2. Okay, that's going to be our law of resistance versus cross-sectional area for wires, I guess. So here's a nice specific example. We got a gauge 24 wire that has a cross-sectional area of 404 circular mils. Okay, we got some stuff going on in that statement. First of all, gauge 24 is just a label. It's not the area. You don't put 24 into any formula. Okay, it's just a label. It's a tag. That's all it is. When they tell you over here that the cross-sectional area is so many circular mil, that's the area. That's the area right there. Now, another question. What the heck is a circular mil? A circular mil means if you had a wire that had 1 mil, what's a mil? It's 0.001 inches. So if you had a 1 mil wire, a 1 mil diameter wire, this area is called a circular mil. It has an area of, let's be a little bit neater. Maybe I should edit this, right? Area of 1. Who knows what the area really is? You'd have to use pi r squared and stuff to get the actual area. But they say, don't worry about it. We're just going to call it a circular mil. Area of 1 circular mil. Okay, so it's not square inches or anything. It's just a made-up thing. It's like, hey, if you had a 1 mil wire, we'll say that area, we'll just call that a circular mil. Okay, so if it's 404 circular mils, here's where it's a good idea. This is what makes it a good concept. It's 404. It's kind of like saying I got a bundle of 404 1 mil wires, right? So gauge 24 is the equivalent of having 404 wires that are all 1 mil in diameter, which is really small, by the way. But anyway, that's why it's a useful unit, circular mils. So this is like having 404 wires that are 1 mil in diameter. This is like having a bundle of 1,600 of those wires that are 1 mil in diameter. So notice when the gauge went down, the area went up. That's interesting, right? So again, don't pay attention to gauge. You don't put, or pay attention to it, but don't put it into any formula. Don't be putting it into any formula. Okay, what do you say we answer the question now? So it says, okay, we got a certain length of gauge 24 wire with a resistance of 840 mils. So first of all, since this is an inversely proportional situation, we're going to take the area of the gauge 24 times the resistance of the gauge 24. Okay, what would be the resistance for the same length of gauge 18? Well, the area of gauge 18 times the resistance of gauge 18. Those will be the same. That's using basically this. Instead of 1, 2, I'm using the gauge number. So the area of gauge 24 times the resistance of the gauge 24 is the same as the Same as the area of the gauge 18 times the resistance of gauge 18. Now, they told us here, gauge 24, resistance 840. Okay, that goes here. 840, and those are called milliohms, which means 1,000th of an ohm. Now, the area of gauge 24 we have to get from up here. It says here that gauge 24 has an area of 404 circular mils. So that's what goes in here. Okay, cool. That's the left side. Do we know the area for gauge 18 wire? And we do. It says it right there. Gauge 18 wire has 1624 circular mils. So notice we can solve for this now. Cool. So you take the 404, you multiply it by the 840, and then at some point you have to divide both sides by 1624. Right? So on your calculator, you're simply typing 404 times the 840, and then you're dividing by the 1624, and what we end up with here is just about 209 milliohms. Okay, so this is kind of the main thing to focus on right here. You want to be comparing the resistances of two wires that have different thicknesses to them, different diameters to them, different gauge wires. You can just kind of use a setup like that because the area and the resistance are inversely proportional. It's a multiply setup. Hey, why don't you try this one yourself? Gauge 12 wire. You might have to use some of the data from the previous problem, but a gauge 12 wire has that area and a resistance. So what's the resistance for the same length of gauge 24? Pardon me. Coffee's still too hot. Anyway, I've paused. You've paused. Now you're back. Okay, here we go. Gauge 12 wire. Okay, so the area for gauge 12 times the resistance for gauge 12 is going to be the same as the area for gauge 24 times the resistance of gauge 24. Now this assumes that the length is the same, right? If you go changing the length, this doesn't going to work. Exclamation point, length is the same. But gauge 12 wire has a cross-section area of 6530. Cool. And the given length of this same wire has 3.4 ohms. Cool. Gauge 24 wire. Well, they didn't tell us the area of the gauge 24 wire, but that's okay. They did up here. Gauge 24 wire. There it is. 404. Bring that down. 404 circular mils. And now we can solve for the new resistance. Beauty. So on your calculator, you just go 6530, you multiply it by the 3.4, and then you divide both sides by the 404, the reasoning being that you're trying to cancel it off the x there. So it looks like this if you don't push the buttons right away. Anyway, you get an answer of I'm going to say 55 ohms. I think I got like 54.96 or something. So it's just about 55 ohms. Cool. Resistance is inversely proportional to area. There's how you can solve those problems. There's other things that are inversely proportional, like transformers. Now, remember in the last lesson, we were talking about transformers, and we said that for voltage is directly proportional to the number of turns. Well, this is saying the current is inversely proportional. So that's kind of interesting. The current and the voltage have opposite properties, whatever you want to call it, is inversely. They behave differently. Opposite behaviors. Inversely proportional to number of turns. So another way to phrase all this is to say the side with more turns more voltage. That's what directly proportional means. More turns, more voltage. The side with more turns has the bigger voltage. Remember, you've got a primary side and a secondary side to this thing, right? So when I say the side with more voltage, what I mean is if this side has more turns than this side, this is going to have a big voltage. This is going to have a little voltage because this has got the big turns. Whereas it's the opposite. So the side with more turns has the bigger voltage and the smaller current. Now, I stands for current. So if I were to This one has more turns. It's going to have a little current. This only has a couple turns. It's going to have the bigger current. So they vary in opposite directions is what I'm trying to say. So let's get, oops, I didn't want to erase all of that. Let's just get this picture out of the way because it's getting a little sloppy there. Okay, so we just want to, basically, how do we solve this problem here? Okay, the current is inversely proportional tells us that we're going to use one of these kinds of setups. Current is going to be, let's put it this way, current times the number of turns. Not like last time where we put voltage over the number of turns. That was last time. That was a direct proportion. This is an inverse proportion, so we do the multiply setup. So the current times the number of turns, that stays the same. It's on the primary side. You're going to, on the primary side of the transformer, you'll have a certain current and a certain number of turns, and then on the secondary side of your transformer, you'll have a different current, a different number of turns, and those are gonna, when you multiply, it's the same. Those products are gonna be the same. So, looking at our problem, primary side measures 14 amps. There we go, folks, 14 amps. And of course, that's what we're solving for is on this side, right? What's the current on the other side? Now, when they say the turns ratio is 4:1, that always means primary to secondary. They always state it, primary to secondary. So a turns ratio of 4:1 looks like this, 4:1 turns ratio. So good. Now, if you solve that equation, it's not much of an equation. On the left side, 14 times 4 is 56, and on the right time, x times 1 is x. And so it's 56. We will have 56 amps on the other side. Does this match our expectations? Well, if the turns are going down, the current should go up. That's what inversely proportional means. So we went down, basically we divided by 4, right? 4 divided by 4 is 1. So this is multiplied by 4 to give us 56. So yes, it matches our expectations. Cool. One more. Whoops, where are you going? One more. We got a nice parallel circuit here. So compare this to last time. We were playing with two resistors in series, and we said that if you measured the voltage across each of them, the voltage was directly proportional to the resistance. Okay. Well, this is not the same kind of setup. This is what we call a parallel circuit, and it turns out that the key thing, I guess, one of the main properties of a parallel circuit is, well, they're saying it right here, is that the current through a resistor will be inversely proportional to its resistance. So the current goes through, right? So there's a certain current coming through here. I'm going to call that I sub 1 or something. And this is our R sub 1. And then there's a certain current coming through this one too. I'm going to call that I sub 2 or something. So when we say they're inversely proportional, what we mean is that the current through the first resistor times the resistance of the first resistor. You know what? We know what it is. Why don't I just put the number in? So the current through the first resistor times its resistance, 50 ohms, is the same as the current through the other resistor times its resistance, 100 ohms. So those are the same. Cool. Now, we got something that makes this a little tougher than when we were playing with voltages. So let me just kind of put this up as a warning, perhaps. How should I say this? P.S. You cannot just add these resistors. You cannot just say that, oh, I got 100 ohms there and 50 ohms there, that's 150 ohms. It doesn't work. It worked if they're in like this, series. If you have 50 here and 100 here, that does add to 150 ohms. But these are not arranged like that. These are arranged differently. It doesn't work that way. There is a funky formula that you'll probably see in your DC AC course at some point. But I don't want to do the funky formula. I'm focusing on proportions here. So, this is true. This is true. Okay. Now, we're running into a problem, of course, because how do we solve it? Well, you got the 4 amps coming through, but the thing is the 4 amps is kind of splitting. Some of it goes this way, some of it goes this way. You can't say that this is 4 amps. You can't say that this is 4 amps. They're not, in fact. They add up to 4 amps because, you know, like I say, you had 4 amps coming in, and then it's split into 2 parts. Now, I don't know if in fact, it's not going to be 2 amps and 2 amps. It would be 2 amps and 2 amps if these were both 50 ohms, or if these were both 100 ohms. If they both had the same resistance, then yeah, it would split equally like that. But they don't have the same resistance, so it's not going to split equally. In fact, what does it mean when we say inversely proportional? It means the bigger resistor is going to have less current, right? As the resistance gets bigger, the current goes down. That makes sense, doesn't it? The bigger resistor has less current. Who wants to go through the big resistance? Go through the little resistance. Take the path of least resistance. If this is the small resistor, it's gonna be easier to go this way, and so more of your current is gonna go that way. Okay, so back to our problem of how we're going to figure this out. Well, what I just said was that those 2 currents add up to 4. Let's be a little more neat here. Those 2 currents add up to 4. Aha! See, now I've got 2 equations. And when you have 2 equations, you can usually figure out what the two unknowns are. So what I'm going to do, let's see, how should I do this? You could take a million approaches right here. I think what I'm going to do is a method that's called substitution. In fact, let's go like this. And we won't really have to do much of this until later in the course, like way after our first test and everything. But you might as well start getting a flavor for this now. Substitution. What I do is I take, let's call that equation 1 and call that equation 2. So I'm going to rearrange equation 2 to look like this. I'm going to subtract I sub 2 on both sides. Okay, now remember the subscripts, you don't do math with the subscripts, they're just labels. So I sub 1 just means current number 1, and I sub 2 just means current number 2. Anyway, I rearranged equation 2. What I do, I subtracted this on both sides, right? So take away I2, it's gone over here. Take away I2, and it looks like this. Okay, so I1 is the same as 4 minus I2. Now, plug that into equation 1. So maybe I'll get a different color. Plug this in. Plug it in. Yeah. In other words, I1 is the same as this. So I can come up here where it says I1 and I can make that switcheroo. Just like tag team wrestling. Tag, the I1's out, the 4 minus I2 is in. So what's my equation look like now? The left side looks like this. 4 minus I sub 2 times 50. And the other side, why don't we just call that a 100 I sub 2. Now, if you don't mind, I'm just going to swap these around, right? This says that we're multiplying 2 things together. And would you admit that 3 times 4 and 4 times 3, it doesn't matter which way you do it, you're going to get 12, right? Multiplying doesn't matter what order you go. So I'm switching the order just because this is easier for me to look at. Now, this is a thing called distributing. 50 times 4 is 200, and then 50 times this is a minus 50 times I sub 2 equals a 100 I sub 2. I want to solve for I sub 2, so I want all my I sub 2 on the same side of the equation. So I'm adding 50 I sub 2 on both sides. So the left side is a 200, and the right side is now a 150 I sub 2. Almost there. So actually, we've kind of seen this maneuver before. If x was on the right and it was being multiplied by 150, what we had to do was divide both sides by 150 to cancel it off. And here we have an answer. 200 over 150 is, I believe, 1 1/3, isn't it? Yeah. Or 1.333. In fact, let's just call it 1.333. 1.33. So the current I sub 2, where's that on my thing here? That would be this one. This current is 1.33, right? I want it to show up. 1.33 amps is going this way. Now, they add to 4, so you can just go 4 take away. This is 2.67 amps coming through this side. Meet with your expectation? It does, because, again, Stop, go away. What are you doing? Stop, go away. Go. Why is this here? Go away, go away. Go. Sheesh. Anyway, so like I was saying, yeah. So the bigger resistor here has less current going through it. The smaller resistor has more current through it. That's the nature of an inverse proportion, an inverse relationship. Okay, so I hope that was kind of cool looking at that. This is like algebra type stuff, right? Just a little bit of algebra in this course. Like I say, more in the next unit, not this unit, but I like to plant seeds. Okay, enjoy your inverse proportion practice. Make sure you keep your eye out when you look at a problem. Is this a direct or is this an inverse? Because I'm not promising that just because it's on your inverse homework that it's an inverse proportion. Keep your eye out. Make sure you're always trying to figure out what's the difference.